So now voltage E g is then given by magnitude E g angle delta is equal to magnitude your voltage V 2 angle 0 plus j x e q I. Actually, the circuit diagram, I mean if you make it like a circuit. So, this is your one bus bar, this is your infinite bus, the equivalent this thing, and this is your angle E g delta, and current flowing through this is I, it is j x q, and this is V 2 angle 0. So, that is the equivalent circuit if we do like this, because x q x e q we have got 0.5 here. So, this way if this way the current I also computed, right. This way if you make it, then your magnitude E g angle delta, you can write magnitude V 2 angle 0 degree plus j x e q into I. But we know that magnitude V 2 is given 1 and x e q we got 0.5 and I also you have got this value. If you put it, you will get magnitude E g angle delta is equal to 1.463 angle your 20 degree. Therefore, voltage magnitude 1.463 per unit E g and delta is equal to 20 degree. And next is that P is equal to E g into V t upon x q x e q sin delta. Therefore, P is equal to E g is 1.463 into 1, x e q is 0.5 sin delta. That means, P is equal to 2.926 sin delta. Now, from equation 20, this is the equation h upon 5 d square delta dt square is equal to P I minus P. This is from equation 20. Now, if it is desired to work in electrical degrees, then this equation 1, I mean we are repeating equation 20, right, that is h upon 180 f into d square delta upon dt square is equal to P I minus P. This is equation 2 say. Now, P I here P I is equal to 1.0 per unit mechanical power input to the generator. Therefore, this can be written as h is by 180 f into d square delta dt square is equal to 1 minus 2.926 sin delta. So, as a verification, right, at steady state your at steady state you will find that 1 minus 2.926 sin delta is equal to 0, and if you compute delta, delta will become 20 degree, and there also we have got this here also we have got delta is equal to 20 degree. So, this is that swing equation, and here also you will get as a verification of the result at steady state P I is equal to P is equal to 1. Therefore, 2.926 sin delta is equal to 1. Therefore, delta is equal to 20 degree, right. So, now example 6, it is given that find the maximum steady state power capability of a system consisting of a generator equivalent reactance of 0.4 per unit connected to an infinite bus through a series reactance of 1 per unit. The terminal voltage of the generator is held at 1.10 per unit and the voltage of the infinite bus is 1 per unit. That means, if you put that all this language in the diagram, that how it is given, that equivalent circuit of the system. So, it is actually it is that generator voltage that is your E g angle delta, and this is given your what you call generator equivalent reactance 0.4 per unit. So, this is x d we are writing say 0.4, and your through a series reactance of 1 per unit. So, this series reactance here it is 1 per unit, and terminal voltage it is given 1.10 your magnitude. So, we are writing V t is equal to 1.1 angle theta, and infinite voltage bus voltage is given, it is 1 angle 0, right. So, you have to find out the maximum steady state power capability. So, this whatever has been your mentioned here, we are putting in this diagram. Now, and what you will do that first you apply your what you call KVA your KVL in this. So, it is your magnitude E g angle delta is equal to your j x d I, j x d into current flowing through this is I plus V t, right. This is one equation. Similarly, I is equal to, you can write here, I is equal to, you can write V t minus V divided by x, this is this x, I mean here. So, I is equal to, you can write V t minus V upon x, that means we can write I is equal to V t minus V upon your reactance, it is, so j x, right. So, I is equal to 1.1 angle theta minus 1 angle 0 divided by j 1. So, now this equation, using equation 1 and 2, that means this I you substitute here, if you do so, and then your magnitude E g angle delta, again and again not calling magnitude, understandable, E g angle delta is equal to 1.1 angle theta plus j 0.4, 1.1 angle theta minus 1 upon j 1. If you simplify this, you will get angle E g, your E g angle delta is equal to 1.54 cos theta minus 0.4 plus j 1.54 sin theta. This is equation 3. Now, maximum steady state power capability limit can be reached when delta is equal to 90 degree. That means, real part must be 0. If real part 0, then delta will become 90 degree, right. So, that is that means, if you put this one, real part is equal to 0, then you will get the theta value. So, that means 1.54 cos theta minus 0.4 is equal to 0, therefore, you will get theta is equal to 74.9 degree. So, that means, if this part is 0, then magnitude E g actually will become 1.54 sin theta. So, that is why magnitude of E g is equal to 1.54 sin theta is equal to 74.9 degree. That means, you will get magnitude is 1.486 per unit. That means, V t is equal to, actually 1.1 angle theta. So, theta we have got. So, V t is equal to 1.1 angle 74.9 degree. That means, P max is equal to E g into V divided by x d plus x, that is your here magnitude E g into V divided by x d plus x, the whole reactance of the line. So, it is actually 1.486 into 1 divided by 0.4 plus 1, that is equal to 1.061 per unit. So, with that we have taken few examples from the point of view of swing equation as well as steady state stability. Next, we will come to the equal area criterion. Now, a solution to the swing equation for delta t, delta is a function of t, leads to the determination of the stability of a single machine operating as a part of large power system. That means, for whenever you try to this thing, your solution for swing equation, you have to go for some iterative technique, right. Leads to a determination of the stability of a single machine operating as a part of large power system, but we will see some that your what you call that equal area criterion. So, however, solution of swing equation is not always necessary, right, to investigate the system stability, all the time we do not. So, rather in some cases a direct approach may be taken. Such an approach is based on equal area criterion. For example, just come to that, consider equation 18, that m d square delta d t square is equal to p I minus p is the acceleration power, accelerating power. That means, d square delta d t square is equal to p a upon m, this is equation 39. Now, if your that this is delta and this is t, if that graph delta versus time graph moves like this, then system is unstable, but if it oscillates and die out, then at any point the d delta by dt will be 0. So, as shown in figure 6, in an unstable system, delta increases in your indefinitely, it is continuously increasing with time and machine lose synchronism. So, it is unstable system, because delta is continuously increasing, but if in a stable system delta undergoes oscillation, that means, in a stable system which undergoes oscillation, which eventually die out due to damping. So, it will go like this and finally, it will die, or what you call that oscillation will die out due to damping. So, from that it is from this it is clear that it must be your what you call for a stable system, that at some point d delta by dt has to be 0, right. This criterion can simply be obtained from equation 39, from this one, that if d delta by dt is 0, like this, then system will become stable. It will oscillate and finally, the oscillation will die out. So multiply equation 39, that means this equation both side you multiply by 2 into d delta by dt. So, if we multiply this 2 delta by dt on both side, then 2 d delta dt into d square delta dt square is equal to 2 p I m into d delta by dt. So, left hand side can be written as d dt of d delta by dt whole square. If you take its derivative, it will come like this. So, we are writing d dt of d delta by dt whole square is equal to 2 p a upon m into d delta by dt. This is equation 40. So, that means which upon integration, if you integrate this, this equation 40, then it will be d delta by dt whole square is equal to 2 by m your delta 0 to some angle say delta into p a into d delta. This is equation 41. So, or d delta by dt is equal to your root over 2 by m delta 0 to delta p a delta. This is equation 41 a. Now, this is 41, this is 41 a. Now, this equation 41 a actually gives the relative speed of the machine with respect to the synchronously revolving reference frame. We assume somewhere that delta is equal to theta e minus omega s t. That means, d delta by dt is equal to your d theta e dt minus omega s, right. So, that means, the same thing, it gives the relative speed of the machine with respect to the synchronously revolving reference frame. So, for stability, the speed must become 0, that means, d delta by dt it must be equal to 0, right. So, that means, at some time after the disturbance, that means, your what you call, therefore, from equation 41 a we have for the stability case. So, for stability the speed must become 0 at some time after the disturbance. That means, I showed this graph that for stability somewhere d delta by dt has to be 0. So, in that case, therefore, from equation 40, if d delta by dt 0, then integral of delta 0 to delta p a d delta it can be written as 0. Therefore, we can write this, that delta 0 to delta p a delta is equal to 0, say this is equation 42, right. Now, you consider the machine, that now we will come to that what is equal area criterion. So, you consider the machine operating at the equilibrium point delta 0. This is the equilibrium point, that is your delta 0, and corresponding to the mechanical power input p I 0. This is the mechanical power input, this horizontal line, mechanical power p I 0, but we are writing p 0 is equal to p I 0 as shown in figure 7. So, consider a sudden step increase in input power represented by the your horizontal line p I. That means, it was operating at a steady state condition, but suddenly that your input power that increased to your p I. So, here that means, p I greater than p 0 or p I 0, I say p I greater than p 0, suddenly your what we call input power is increased. So, in that case, and p I greater than your this p I then greater than your p 0, then that means, the accelerating power on the rotor is positive, right, and the power angle delta increases. So, as soon as your, because p I your this p I actually your greater than your p 0, the accelerating power on the rotor is positive, and the power angle delta increases, because delta now will increase, So, what will happen, that excess energy stored in the rotor during the initial acceleration is it will be delta 0 to delta 1, that is your delta, this diagram, that delta 0 to delta 1, because it has increased from your suddenly to p I. So, this is the horizontal line, it is cutting here this sine curve, that is your power curve at this point, that is B, right. So, whenever that means delta 0 to delta 1, that is that excess energy stored in the rotor due to the initial acceleration, that p I minus p delta, that is area A B D, that is this area A 1, area A B D, right, and that can be is equal to I am writing area A 1, or delta 0 to delta 1 is p I and p is equal to p max sin delta. So, we are writing p I minus p max sin delta d delta, this is area A 1, right. So, this is I am marking as equation 42. This is that excess energy stored in the rotor during the initial acceleration, because as soon as this p I suddenly load has increased, input power increased to p I, then rotor will start accelerating. So, that means your what you call this excess energy stored will be only this area, you have to find out A 1. Similarly, with the increase in delta, the electrical power increases, because as delta is increasing, then electrical power P also will increase, So, electrical power increases, and when delta is equal to delta 1, right, I mean this value, when delta is equal to delta 1, right, the electrical power matches the new input power P I. That means, when delta is equal to delta 1, you will get P is equal to P max sin delta 1, that means at that time your P I will become P max sin delta 1, it matches your the new input power P I. So, if it is so, even though that means at this point, at this point your accelerating power is 0, at this point, because P I when it is coming to this point, P I is becoming your P is becoming P max sin delta 1 when delta is equal to delta 1. So, at that time P I will be I can say this is my P 1 P max sin delta I have written, when delta is equal to delta 1, P 1 is equal to P max sin delta 1, at this point P I is equal to P 1. So, it is your that means P accelerating power is 0 at this point if it matches. So, that is why that electrical that is the electrical power matches the new input power P I. So, in this case, even though the accelerating power is 0, at this point the rotor is running actually above the synchronous speed, because it was accelerating, although at this point that your this power is equal to that electrical power matching with this input power, but rotor is accelerating. So, it is running above the synchronous speed. So, that means what will happen, the hence delta and electrical power P will continue to increase. So, your delta will continue to increase. So, P also will increase, the electrical power continuously will increase, but how far. So, it will happen. Now, what will happen, as it is as rotor is above the synchronous speed, and as it is your what you call that means it is continuously the delta will increase, that means that P at that time if delta 1 is increasing, that means P will be greater than P I, at that time P will be greater than P I, because at this any point here P will be greater than P I, then what will happen, rotor will start decelerating till it achieves its synchronous speed, say at point C. That means, the rotor is running above synchronous speed, hence delta and electrical power P will continue to increase. That is why I am telling. Now, when P I less than P negative, so when P I less than negative, the rotor will decelerate, right. Consider the rotor to decelerate towards synchronous speed until delta is equal to delta 2. When it achieves here delta is equal to delta 2, right, that it reaches to synchronous speed, that is your say at point C. So, until delta is equal to delta 2. So, according to equation 42, that means your this equation, according to equation 42, this equation, the rotor must swing past point B until an equal amount of energy is given up by the rotating mass. Up to this, it was energy was stored, right, and it will reach to a point, it will still oscillate and it will pass point B until a point, that is when delta is equal to delta 2, it will your what you call it will your until an equal amount of energy is given up by the rotating masses. Then whatever energy stored, same amount of energy will be given up, right, till it reaches at point delta is equal to delta 2. So, the energy given up by the rotor as it decelerates back to synchronous speed is your this one. So, the energy given up by the rotor as it decelerates back to synchronous speed, it can be given as your delta your P, because at that time your P is greater than P I. So, it is integration will be delta 1 to delta 2, and it will be the integration of the P E minus P I d delta is equal to area B C E, area is equal to area this area A 2 B C E, right, is equal to area A 2. Actually, somewhere you can also write some book also you can find the decelerating energy, you will find somewhere they are also writing delta 1 to delta 2, they are writing P I minus P d delta, that means area will be this area will become negative. After that they are taking that absolute of area 1 is equal to absolute of area 2, that is also true, but directly we are writing in that case if you take that P I minus P, decelerating means it will become negative, right, and here it is storing. So, it will be positive, and when it is your what you call a decelerating side, it will become negative. That so, that means your, but here we have written delta 1 to delta P minus P I d delta, that is area B C E is equal to area A 2. This is equation say 42b. Now, result is that the rotor swings to point B and the angle delta 2, that means rotor will swing till delta 2, right, and this area delta 2 that area 1 must be equal to area 2. So, this area 1 must be equal to area 2, because I said the rotor must swing past point B until an equal amount of energy is given up by the rotating masses. So, in that case it will be area 1 is equal to area 2, this equation I am giving 42c. Now, what is the basic philosophy? That suddenly power has increased to P I. So, in that case what will happen, that P I will be greater than P 0. So, rotor will start accelerating, and when it is accelerating it will come to a point when delta is equal to delta 1. At that time P I is equal to your this P is equal to P I, that means accelerating power is 0, and at this time it is rotor is storing energy. Now, at this point the rotor is running above synchronous speed, that means rotor will continue to that the delta will continue to increase, because it is running your above synchronous speed till the point say C, that is delta 2, and until it give up the equal amount of energy as it is A 1. So, it is going up to C. So, this way this is accelerating energy, this is decelerating energy, both have to be equal. So, area A 1 must be equal to area 2, but question is that is up to the synchronous speed till it reaches to synchronous speed. So, ultimately what will happen, that area 1 must be, this is known actually equal area criterion. So, this is area 1 and this is area 2. Actually it will swing back and forth, and because of the machine damping, finally after some time it will settle to point B. So, this is the rotor angle would then oscillate back and forth between delta 0 and delta 2. I told you between delta 0 and delta 2 it will be swing back and forth, and finally and it at its natural frequency. So, as damping present in the machine, right, will cause these oscillations to subside, and new your what you call new steady state operation would be established at point B. After some time this will oscillate, right, back and forth, finally it will be stable at this point B. So, this is actually is called equal area criterion. So, I hope this part is understandable, right. So, idea is that when it is going past to up to this, that power has increased to P I, and then it is accelerating, but it is above synchronous speed. So, it is further it will your accelerate, but still it achieves to synchronous speed. At that time P greater than your what you call P I. So, it will decelerate, right, and finally it will achieve a point your delta 2. So, this is actually power angle characteristic of the your machine. Therefore, if area 1 is equal to area 2, right, the area 1 is equal to area 2, then this we can write all these equations shown that delta 0 delta 1 is equal to p I minus p max sin delta d delta is equal to integral delta 1 to delta 2 p max sin delta minus p I d delta. This is equation 43. Now, if you integrate and if you simplify, it will come like this: p I into delta 1 minus delta 0 plus p max cos delta 1 minus cos delta 0 is equal to p I into delta 1 minus delta 2 plus p max into cos delta 1 minus cos delta 2. This is equation 44, but p I is equal to p max sin delta 1 from this equation, that p I here p I is equal to when delta is equal to delta 1, p I will be p max sin delta 1. So, if you substitute here p I is equal to p max sin delta 1, and if you put it here and simplify, it will become p max delta 1 minus delta 0 into sin delta 1 plus p max cosine delta 1 minus cosine delta 0 is equal to p max delta 1 minus delta 2 sin delta 1 plus p max cos cosine delta 1 minus cosine delta 2. This is equation 45. If you simplify this, something will be cancelled, right. I am giving you the final form. If you simplify this, then it will become that delta 2 minus delta 0 sin delta 1 plus cos delta 2 minus cos delta 0 is equal to 0. This is equation 46. So, this one actually that equal area criterion, whatever you have got, different conditions are there, So, for this thing, although we will solve in the next thing next class, but I am giving you a synchronous generator capable of developing 500 megawatt power, 500 megawatt power per phase, operates at a power angle of say 8 degree. By how much can the input shaft power be increased, right, suddenly without loss of stability? Assume that P max will remain constant. Somewhere you will find this kind of problem has been taken as a mathematical development, but what we will do it, that we have taken this one, right. So, maximum will be your what you call that this is P 0, suddenly it has increased to P I, and this is that maximum angle it can go up to delta m. If it goes somewhere, I mean more than delta m, then what will happen? P will be less than your P I, system will become unstable. So, I will come to that. So, P 0 is equal to P delta 0 8 degree, P 0 is equal to P max sin delta 0, that is it is coming 69.6 megawatt. Now, delta m be the power angle to which the rotor can swing before losing synchronous, this is the maximum one can go, right. If this angle is exceed P I, I mean if it comes somewhere here say, then it will that again it be that P will be your what you call that P I will be again become that P I will be greater than your P, because if it comes somewhere here, if it goes below that, then P I will be greater somewhere, P I somewhere here, P I will be greater than P, right, and rotor will again be accelerated and it will lose synchronism. So, maximum it can go up to this delta m, P this your delta is equal to delta m, and you have to find out this delta m. So, your P I cannot be greater than your P. If it goes more than delta m, then it will start accelerating and system will your go out of your what you call step, right. So, this is power angle characteristic of this one. Now, from this figure only and this equation we have derived that, therefore, the equal area criteria requires that equation 46, that means in this equation, equation 46, what you will do is that from this graph delta m is equal to pi minus your delta, this is a sine curve. So, from symmetry delta m is equal to pi minus your delta 1, because this is pi, this is your what you call pi. So, it will be pi minus your delta 1. So, this delta m is equal to pi minus delta 1, that means in this equation actually in this equation that delta 2 is equal to delta m is equal to your pi minus your delta 1. So, basically this what you call here we have gone up to delta 2, but up to this it can come up to this delta m. So, delta 2 is equal to delta m actually your what you call this so instead of in this equation, the delta 2 actually is equal to delta m is equal to pi minus your delta 1. So, that is for your understanding such that you should not make any this thing, this actually is equal to say delta 2. So, this delta 2 is equal to in this equation 46 you please put pi minus delta 1, because in this equation it is up to delta 2 in this figure, but it can go up to your maximum delta m, delta 1 to delta m. So, that is why for your understanding I am writing this is delta 2. So, put here pi minus delta 1. So, here also delta 2 you put pi minus delta 1 minus cos delta 0. So, if you do so, then as delta 0 is equal to 8 degree is equal to 0.139 radian. So, approximately 0.14, and equation 1 if you put that. So, if you put all these values, then you will get 3 minus pi 3.14 and it is approximately 0.14. So, it is 3 approximately I am taking minus delta 1 into sin delta 1 minus cosine delta 1 minus 0.99 is equal to 0. Then the delta 1 is approximately 50 degree. So, again repeat the delta m is nothing but delta 2, in the delta 2 is that previous figure equal area criterion, right. So, with that P f this one P E f, right, just where is diagram has gone, that just let me see your, but anyway the diagram here P E f here diagram is here P f is equal to P max sin delta 1. So, it is delta is equal to delta 1. So, P max sin delta 1. So, 500 sin 50. So, 383.02 megawatt. So, initial power delivered by the machine was 69.6 megawatt, that was at this point we computed 69.6 megawatt, and now hence without loss of stability the system can accommodate a sudden increase of P f minus P 0, that is 383.02 minus 69.6. So, this is your 383.02 minus 69. So, that is 313.42 megawatt per phase. So, if it is a 3 phase multiply by 3, it will become 940.3 megawatt of the your input shaft power. Only once again before closing this lecture, that it cannot be more than your delta m, then P I will become P, because any point as you take P I will become greater than P, then machine will start accelerating and it will lose synchronism. So, with that, thank you.